Folks on Zoom, can you hear me? See the screen? All right. Testing. All right, let's start. Thank you for your patience for waiting me for walking down to here. Yeah. So today we will learn about like a virtual memory and a little bit of like the protected mode, and also for the basic concept about the virtual memory. So so in lab one, you just worked on the boot process and then do very little bit of thing that you can later utilize for the debugging. So the monitor feature will let you know how your like a function called stack having been constructed, so that you can identify like which part of the code you need to take a look at the monitor. Yeah. So we ask the developing that first to get familiarized to the JAWS environment, but the actual development for the operating system will start in lab 2, and then that lab 2 is for like building the virtual memory system for JAWS. And before doing that, let's do a little bit of recap about that. So we learned about how we can translate this real mode segmentation. So the segmentation is required because like the all-day CPUs, they only have 16-bit registers. So we need to have the two registers of the 16 bits to indicate like 20-bit addresses. And to do that, it has a very easy calculation. So there is a segment and offset pair. And whenever we see these kind of addresses, and in the real mode, what we can do is we can multiply the segment number by 16 and add the offset. And then the multiply by 16 for the hexadecimal numbers is like just adding 0 at the end. And then in binary numbers, it's equivalent to adding 4 zeros because the 16 is 2 to the 4. Yeah. So you can imagine that like it's like shifting 4 bits. So that's why we can indicate 20 bits by using two 16-bit registers. 16 shifted by 4. Yeah, that will take like the topmost digit will take the 16 to 20 bit in the address. And in our boot process, so what we do is like the BIOS will let the CPU run the BIOS code at this address FFFFF0, which is a 16 byte less than the 1 megabyte address, because like they assume that they can always access the 1 megabyte of memory for sure. And then the BIOS will read the first sector of the booting disk, which is called a boot sector or master boot record. And that will be loaded into the physical address 7Z00. So it's the bottommost somewhere in the memory. And then they will run the bootloader. So the bootloader is just a 512 bytes. So it cannot do many things, but it can do the essential things to load the other part of the operating system, and that is so-called kernel. And we expect that in our kernel, we will use the more memory than 1 megabyte. And to do that, we need to follow the following 3 steps. So the first thing is like they enable A20. And then we briefly introduced about what was A20. So A20 is like an address line bit 20. And then why that exists, the reason why we have that kind of feature is that like for the sum of the segment operation, if we have FFFF for the segment, for example, then if we shift that by 16, then that will automatically point to this address. But if we have offset value larger than 16, then that will overflow the 1 megabyte, the value. So for that kind of the overflowing, so the early stage engineers, they want to ignore that kind of overflow, and then like it works as a circular function. Yeah. So A20 means that like the early stage engineers, they totally ignored some of the overflow bits carries for that. So they can conveniently move over the top of the region that stores a BIOS code, and also the bottom of the region that stores a booting code, yeah, from the master boot record, yeah. So by doing so, the early stage engineers don't have to switch the segment number between two, yeah. That's why this kind of feature exists, but in these days we don't need that feature. And then if we ignore the 1 megabyte line, then we almost lost like the half of the memory. Yeah. So that's why we need to enable that. But we don't need any kind of the implementation for that. So what we just need is like just take a look at how the bootloader enables A20. So it has a while loop, and then try to work with some of the IO port using the in and out instructions. And then it will enable the protected mode. And then the protected mode is the mode that enables accessing the memory more than 1 megabyte. And then how the bootloader enables the protected mode is that. So we need to set a so-called data structure called a global descriptor table. And then that global descriptor table is just an 8-byte structure, look like this. And then one of the students asked that, like why the structure is look like this, not the base address 32 bits are like the beautifully concatenated all together. So the reason for that is like in very old days. So it's better to make human work harder than like making the hardware work for human. So like the hardware engineers designed this kind of the data structure for making easier to the hardware to get the data. Yeah. So it depends on how the circuit or like a logics are developed in the CPU, but this kind of data structure is better for the machine, definitely not for the human though. But the beautiful thing about the software is that like we can make some of the macros for you. So in JAWS, how we set up the global descriptor table is something simple like this. So segment null means like that we just put 20. So because we are working on the 32-bit processor, so 20 means that wiping all the 8 bytes as a 64-bit as a 0. And then for the code segment, how we can define it is like this 0 means the base address. And then this seg macro will beautifully spread out all the bits into this kind of the data structure, so that you don't have to worry about matching that kind of data structure at all. But please note that conceptually, you should know that the hardware defines that kind of data structure. So the software developers need to match to that kind of hardware specs. And then that kind of specs are available in the Intel manual, definitely. But we will share the excerpt of such part whenever we need that kind of hardware specification is required for developing JAWS. Yeah. And then the base address is here, and then this is the limit address. But the limit address only has the 20 bits. But I will let you know how we can indicate like the 32-bit range of the limit address in the middle of this lecture. So we will learn about that later. And then after setting the code and data segment and the null segment, and what JAWS bootloader does is enabling the protected mode. And to enable the protected mode, so there is a knobs in the CPU that we can turn on and turn off some of the features of the CPU. And CPU is basically a digital circuit, and then like the turning on means like we set some of the bits as 1, and then turning off means like we set some of the bits as 0. And then that also based on the specification. So like sometimes like setting 0 means some of the enabling the feature, but for protected mode, how we can enable that is, so there is a register called a control register. So it is called the CR control register, and the CR0 of the Intel x86 CPU. And same thing for the AMD, because they follow the x86 architecture. Yeah. For those CPUs, CR0 has like some of the bits that we can enable some features and also disable the features. And then this CR0 PE on, the value of this one is just 1. And then we are getting the CR3 to EAX, and then or 1 to EAX. So what that means is that like we are actually upping the last bit of the CR0 register, so to turn on the protected mode. So I will show what kind of features available in the CR0 register later in this lecture. But what you need to know is we are enabling the feature by setting some of the bits and then putting that back to the control register. So if you want to learn more about what kind of control registers are available, then you can visit this Wikipedia page. And then we will use CR2 and CR3 register later in lab 2 and lab 3 because they do have a different proposal about that. And the last step of the JOS bootloader is that after enabling the protected mode, we can access full 4 GB of range. But the thing is, our QEMU, the emulator, it is set by just using the 128 MB of physical memory. So you will not have the full 4 GB, but at least we can access the over 1 MB region. And after loading the kernel, after enabling the protected mode, what we need to do is we need to run the long jump. And what that means is we are starting and then less CPU to get into the protected mode. So right after, if you follow the instructions in the bootloader, right after these lines of enabling the protected mode, then you will see the long jump instruction to get into the protected mode. And after that, because we can access the more than 1 MB of memory, then we will load the kernel file. And then that is built by GCC by whenever you type a make or make QEMU nox, that kind of command. So that will be formatted in the executable linker format, ELF. And then what this means is that the file has a format that indicates which part of the file contains the assembly of the code, or some other parts of the code contains some of the string literals or some other data structures. And then that kind of thing is defined inside the file. And then the file format is not that complex. And then we only use the part of the file format. So please refer to the some part of the Wikipedia document and also some part of the code. Then you will see that how the kernel is being loaded by reading the ELF header. So it will go over some of the program headers and sections, and then you can see all kind of thing in boot.c. And then make sure that even if the boot.c contains a longer code than a 512 bytes, when it is get compiled and then generated as assembly code, then these are quite small and then can fit into the boot sector, which is 512 bytes. All right, any questions up to this point for the recap? Then I will move on to the next part. So we will learn about the protected mode. Then first, let's take a look at why do we need the protected mode. So the real mode has been used by several operating systems, including MS-DOS, which was very popular in 1980s and 90s. Yeah, I'm not sure how many of you have used that before, but if you played some of the classic game using DOSBox, and then that emulator actually runs a real mode MS-DOS kind of the operating system. And then that operating system was very naive in a sense that providing some of the memory isolation for the security purpose. Then let's think about the case that suppose we have 2 programs would like to run at the same time. So it could be program A and program B, then if we have like a big chunk of the memory, we can put the area for the program A at here and program B at here. Yeah. But the problem is that in the real mode, there's no protection at all. What that means is that suppose the program A, the developer make a mistake or developer maliciously like insert some of the bad code inside there, then if they know what is the address for storing the program B's data and code, they can alter the data and then implement some other malware. Yeah, that's totally possible because no other hardware or CPU restricts from like doing that. So in the real mode, there is no security at all. So that's why Intel developed protected mode starting from the 80386. And then the important thing here is that now the segment and offset access will be totally different in the protected mode. Yeah. So what we will do in the protected mode after enabling the PE0 as 1, yeah. What that is after that. So how we will use the segment and offset pair as, so here the offset is 32-bit because like now we are using the 32-bit processor. So i86 is the first 32-bit processor born in 1985. And then the segment selector will be, so suppose the address is something like this, segment and the offset. Then in the real mode, how we calculate the address was like this multiplied by 16 and then add the thing. So in the real mode, that address will be translated into this one. But after enabling the protected mode, we will not using that kind of translation. CPU will work in a completely different way. And then how it will do is, so this is the selector for the global descriptor table. So you recall that the JAWS defines the table as a 0 as a null segment, and then the offset 8, it will be having the code segment, and offset 16, it will have a data segment. And what it will do is like the selector, the segment selector will refer to the index in the global descriptor table. So it must be the multiple of 8 because our global descriptor size is 8 byte. So it could be 0, 8, 16, 24, 32, something like that. Yeah. And then how it will translate the address is that it will fetch the table row indicated by the selector. So if the value is 8, then we will get the row at the index 8 of the global descriptor table. And then we will get the base address and then add that to the offset. So that's how the protected mode addressing is calculated in the CPU. And then another thing that the protected mode does is that the name itself says protected. So it will do some kind of the isolation to restrict the one program cannot access to the other program's memory, something like that. And to do that, we can set the limit. So if we set the limit as 1 kilobyte or something, 1 kilobyte is like a 0x400 as in the hexadecimal, then the offset is definitely bigger than that. So the CPU will reject this kind of the memory access. But if the limit is big enough, bigger than 0x3400, then the CPU will allow that access. So it's something like we can have many sections of the memory and defined as a global descriptor table. We can set the base and the limit. And then we can set another base and the limit. So think about the prior example that I put the 2 programs, then we can set the global descriptor table for program A for their base address and the limit. And then for program B, we can set for their base address and limit. And then if we move with the long jump by switching this segment selector, then like there is no way that they can touch each other. And yeah, one question.
Who is designing the base?
So the operating system developer. So that's why we have a global descriptor table in JAWS. So like for JAWS, we defined it for you, but think about it, you can edit any part of the code. So the operating system developers will decide that. Yeah. And then to get into more details of the bits of the protected mode, so you can regard it as starting from the 0th bit to the 32 and 64 bits. And then you can also take a look at the limits and base addresses are stored in this fashion. But the more important thing is that there are some other bits that we can use for like setting up some of the configurations. And then the most important thing here is that the G bit here on the 55th location of the global descriptor table. And then that is set always 1 to JAWS to enable the setting the limit for the 32-bit. So what does this bit does is, so our limit bits does not have full 32 bits. So we only have 20 bits. But this G bit will decide the granularity about like how we will regard the limit. So, and then if the G bit is 0, then the limit would be the byte granularity. So we can only set like a 20-bit range of the limit. So the maximum limit would be the 1 megabyte then. Yeah. But if we set the G bit as 1, then the CPU will multiply the limit by 4096. So the 4096 is actually shifting 12 bits to left because 4096 is 2 to the 12. And then what that means is that we have 20 bits limit, but if we shift that for 12 bits, then we can indicate full 32-bit range in a 4 kilobyte granularity. Yeah. So yes, question?
The point is 2 to 16.
2 to the 12. Yeah, that's my mistake. Yeah. Thank you for letting me know about that. Yeah. So it should be 12. So 20 plus 12 will be 32. Yeah. So JAWS will automatically set. So the macro of the SEG, yeah, that will automatically set G bit as 1 to indicate like the full 32-bit range for the limit address. Yeah. And then like there's a D bit. We will not use D bit, but I want to explain that. So the D bit actually means that like a 32-bit CPUs, it has a compatibility mode to 16-bit mode. Yeah. And then Intel designed all the CPUs to be backward compatible. Yeah, that's why. And then if we set the D bit as 0, then the CPU will operate fully in 16-bit mode. So when we turn on the computer, yeah, it will operate in like the 16-bit mode. And then when we set the global descriptor table and then launching the long jump, then it will enable D bit as 1. Then it will turn on this 32-bit mode. And then similar thing goes on in the like the 64-bit mode. And then like we use real mode for 16-bit, protected mode for 32-bit, and then the 64-bit mode is so-called long mode. Yeah. And then there's a bits that we can also set that to enable the 64-bit mode for the CPU, but we will not cover that in here because JAWS will be like fully in 32-bit. And then here, the R and X bits are like indicating that whether the section is readable and also that is executable. CPU will work according to those bits. So for example, for the code segment, we need to make it as executable and readable. And then for the data segment, we need to make it as a writable and readable. Yeah. So these 2 bits are not that important for the security purpose, but not that important for the when you are developing JAWS. But the another important part is like the DPL, so the data privilege level, and then DPL has 2 bits because the Intel CPU has like 4 level of the privilege mode. But this is an old design, but the modern operating system only uses like the 0 and 3. So the 0 means that the highest privilege, and then 3 means the lowest privilege. And then this is important because I believe like right now, your computers, if that is not Apple M1 processor, Intel or AMD, so your operating system runs on the privilege level 0, while all the other applications, for example, if you're running Google Chrome or VS Code, that kind of editor, yeah, they all will running in the lowest privilege level. And then what that means is that we can set some part of the memory can only be accessed by privilege level 0. So no matter what your applications, for example, Google Chrome does something, they have the area on the computer that they can never access because they don't have privilege. So that's how we can protect the operating system from the other applications. So the memory segmentation will totally be changed in the new memory model. So after we enable the protected mode, how can we load the 2 programs in a separated, isolated region is something like this. So let's take a look at this program A. So it starts with the address 8000000 and then 1 megabyte up here. And then we can define the area of the program A, something like this. So we can set the 32-bit base address as the base address of the program A, and then limit address as FFFF, which is a maximum bit, all bit 1 for the 20 bits. Yeah. Then it will allow from 0 to 1 megabyte region, starting from this base address. And then please note that the G bit, the granularity bit is 0. That means that our limit will be honored as a byte granularity. That's why it only allows like the 1 megabyte from the base address. And then to be in the program A, what we need to do is we need to do long jump to the CS register number 16 to use this region of the memory. And then take a look at the program B, and then we can isolate the program B from program A by having another global descriptor table. So this base and limit address will limit the capability of what program A can access. So they will be jailed in only to this area. And for program B, we can define the global descriptor table as base address as the base address of the program B. And then we need to access 2 megabyte for this program because the end address is this base plus 2 megabyte. And then to indicate that, the 2 megabytes needs 21 bits for the limit address. And then we cannot put 21 bits. Instead of doing that, we can set the granularity bit as 1. That means we will add 3 zeros because each digit in hexadecimal represents 4 bits. And then we are shifting 12 bits. So we will add 3 zeros, then that will allow we can access up to 2 megabytes. Any questions about the memory access model for reusing the global descriptor table in protected mode? Yes.
Can you explain one more time why the 16 is the 20-bit limit is 0x instead of adding just 1 megabyte?
So FFFFF, that hexadecimal number is 1048575, right? That's the 1 megabyte minus 1. And then that's inclusive. So it will allow us to a base address plus 0 to base address to plus that number. And then So the limit means like it defines the range length. So you can regard the base address plus limit is the range of the memory address space that we can access. But when there's a granularity bit, you need to multiply this by 4096, which is shifting 12 bits. And then that will make us to define the limit address for the full 32-bit. Okay. Yes.
Will it be like if you use all of them?
Yes.
You use a part of the part.
Yes.
How do they deal with the unused memory between the two parts?
So we need to create another global descriptor table to use some other parts, so that we can theoretically create a many global descriptor table to define the multiple segments. But in JAWS, we are not doing that at all. We actually use the full memory and then dedicating that to the kernel directly, because we will use different model of the memory protection. Yeah. And then let's take a little bit of examples as we have gone through the real mode segmentation in last lecture. Yeah. So whenever the CPU sees this kind of the address pair, then it will try to consult the global descriptor index 8, right? And then it will fetch the base address. So the base address is this one, and then it will add the offset, but it will first check the limit address. So the limit address is 8000, but because the G bit is 1, then we add 3 more zeros. So its limit is quite huge. Yeah. And then the offset is 80080, and then the offset is definitely smaller than the limit address, so we can access it. So CPU will grant the access to this address, and then the resulting address will be base address plus the offset. So please note that we are not doing the multiply by 16 at here. So we will fetch the base address by referring to the global descriptor table. That's the most important part. Question? No? Yeah. And then the next example. So we have the segment selector as the 1016. Then we will fetch this row to get the base address. So the base address is this one, and the limit address is 1000 because the G bit is 0, so we will not do any kind of multiplication. And then our offset is 333. Then resulting address is 31310000 plus 333, so this address. And we can access this address because the offset is definitely smaller than the limit. But how about this access? Segment selector 10, then we will fetch the base address. But the limit is 0x1000, which is 4096. But it tries to access 8080, which is definitely over the limit. Then the offset is bigger than the limit, so the CPU will reject the access. Yes.
And just to confirm, so the protected mode uses this global descriptor table to look up the bases and the limits.
Yes.
And then in the real mode, it does not use a table; it just uses math with the
Right.
two register.
Okay. Yes. So when the Intel engineers developed the real mode, they didn't have any concept of that. And then for backward compatibility, they remained that kind of feature. But after turning on the protected mode, the internal logic will use the total different logic, something like this, to calculate the address. Another question in the middle? Yes. So the segment selector is a 0x10. That's number 16. And then global descriptor index at 16, we have the base address, this one. So we fetch that from the table. So what that means is that like whenever you see the segment selector in the protected mode, we should refer to the global descriptor table and then access the table by using the segment selector as the index. Another question. So the global descriptor table is stored in the kernel right now, but it could be anywhere in the memory. So to answer that correctly, so when JAWS bootloader, loads it into the memory, so the bootloader contains some part as like the global descriptor table. So for instance, so this part, this is so-called the bootstrap GDT. So this is the bootstrap, the global descriptor table. And then in JAWS, we put it on the data section of the bootloader. And then we will put that address. So you will see that another like the symbol that the GDT-DESC, so which is somewhere in the 7C00 near there. Yeah. And then we will put that address using the LGDT to let the CPU know that where it is. Yeah. And the next is about the DPL, so the data protected privilege, descriptor privilege level, and then per each descriptor. So descriptor means that each row in the global descriptor table, then we can set the data privilege level. Yeah. And then because it has 2 bits, so we can set the 4 levels, but the engineers in that stage, like they believe that there should be 4 levels, but we evolved that from that and then determined that we only need 2 modes. So how we will use for the data privilege level is we will use the highest privilege, which is a level 0. So it's backward. Yeah. So the level 0 is so-called the ring 0. So I'm not sure why like the system designers have called this kind of the privilege as a ring model, but what that means is like from the core to the outer, from the core, you can access any kind of the outer rings, but from the outer ring, you cannot access inside of the core kind of thing. Yeah. So we will use for the operating system, we will use the ring 0 to store the older parts for the operating system. And then we will use the ring 3 to store any kind of the memory that is used by the application. So you can think it as like the applications at ring 3, they can never access something inside this level. And then this is how we can isolate the operating system from the applications. And then the descriptor privilege level defines the ring level. And then the CPU has the current privilege level. And then another weird thing is like this Intel CPU did not reserve the bits to have like a current privilege level, because in early days, having another register in the CPU requires some number of the transistors, and they would like to optimize that kind of part. So what they did is like the current privilege level is hidden behind the last 2 bits of the CS segment register. I know you will hate that, but to reduce the space, they did that. Yeah. And then the reason why is that, so we will have a global descriptor table. Their index as always multiplied by 8. And what that means is that number 8 is 1000 in the binary number. And then if we multiply that by 2, 3, 4, any kind of integer, then always we will have last 3 bits as a 0. Yeah. That's why they would like to use like the last 2 bits or 3 bits, yeah, for the hiding that kind of privilege level. So what that means is that like whenever we use long jump is the instruction that we can change the code segment register, and then we can set the privilege level. So what that means is that if the code segment CS, its value is 8, then its bit pattern is a 1000, and then the last 2 bits are 0. That means we are in ring 0. And for some cases, we could have the CS register value as a 13. That means 10011. And then how will CPU treat this is like it will mask last 3 bits, that they will regard all that as 0 when accessing the global descriptor table. So even if the CS register value is a 13, it will refer to the 10, the 16 as an index for the global descriptor table entry, but it will get the privilege level from the last 2 bits. So what that means is that like a CS register value 13, that means the CPU is running in ring 3, which is the application mode. Yeah. And then the 0x10 means that they're referring to this one, but running in the ring 0, the operating system privilege. And then also for 0xb, this is 11, so 1011. And then when accessing global descriptor table, CPU will ignore these as all 0. Then it will refer to the index 8, but it will set the privilege. It will get the CPU privilege, the current running execution privilege, as 3. So like that's why all the segment selectors, we don't use these kind of the 3 bits, and then Intel tries to use that as like the indicating some other metadata for that. So the important thing here is that, as I told you, from ring 0, you can access everything. But from ring 3, level 3, you cannot access the memory set as their data privilege level is 0. That's how we protect the operating system from the application for altering any kind of data or something. So what that means is that, so suppose the data, like the segment for the global descriptor entry for 8, yeah, it is set as a DPL 0. And then what that means is that like that we have we need to have like a ring 0 access, the permission level 0 to access this memory. But if we try to read that using this segment selector, because the CPU level is CPL is 3, then CPU will reject this kind of access. But the opposite works. What that means is that like in case if we have a segment selector number as a 10, that's a ring 0. But try to access this one. So this area is set as a DPL 3, but the privilege level 0 can access anything. So the access from like a segment selector 10 to this memory region is allowed. Yeah. And because this privilege switching is quite important, so the only way you can switch the privilege level is in running the long call, long jump, or some other mechanism called interrupt. We will learn about that when we get to week 4. Yeah, but at this time you only know that the instruction long jump, that is the only way to switch the privilege level by switching the CS register value. So what that means is that like there is no valid instruction that you can put AX register value to CS register. So if you try to run it or like try to code it in assembler, then like there is no corresponding opcode, so compilation will fail. Yeah. So even this instruction is not existing. And then another protection is that like even if you use long jump, you can move down for the privilege. So what that means is that, so from current privilege level 0, you can launch long jump to privilege level 3. So from 0 to 3, switching is allowed. But while you are executing in the ring level 3, you cannot long jump into the ring level 0. So that is prohibited, and then CPU will kill that stop at that point. So this is how you can think it as the privilege switching is a one direction, no? So you can move from 0 to 3, but then you cannot move from 3 to 0. Yeah. Then you might be curious about so what it means is we can, while we are running the operating system, we can switch to the application level. Then how can you get back the execution from application to kernel? So that actually happens a lot while running the application. So from switching from 0 to 3 is easy because we can use long jump, but the switching from 3 to 0, we cannot use long jump. And for doing that, we have several other mechanisms called interrupt or system call that the application can hand over their execution to the operating system. And because it involves the privilege switching from the low level to high level, so it should have should have designed this securely. And then we will go over those kind of mechanisms in week 4. And then at this point, just know about there's 2 different ring level, ring 0 and ring 3. And then ring 3 can do anything, but ring 0 can do anything, but the ring 3 is quite limited to access just only the memory set by DPL3. And then the JOS can show that how itself set up all the global descriptor table and then how they use it. And then because we are only running in the kernel for lab 1 and lab 2, so we will not using the DPL or segment privilege at all for this time. So we will use that starting for lab 3. But from the booting code, you can see that the JOS will set up the code segment as from 0 to FFFFFFF, but it's actually only has a 5 app, but it will have the granularity as a bit as a 1. And then same thing has been applied to the data segment, but the difference is that for the code segment, it's executable and readable. And then for the data segment, it is set as writable, but the writable implies that it also be readable. So that's why it only has a 1 flag for it. So although the macro lets you beautifully set the flag and then other values, but it will spread the bits according to the Intel's data global descriptor data specification. So to visualize this kind of setup, it's something like segment 8. So this is segment 0, 8, 16, because each row will take 8 bytes. So 0 will be null. So we just put 0, 0, 0, everything. And then for the code segment, it will be 0 to the end, G-bit as 1 to indicate the full 32-bit, and then executable and readable. And then you can refer to some of the bitwise map for the global descriptor table to get the X and R bits. And then DPL is 0. And then for the data segment, so it's at the index 16. And then from 0 to the end of the 32-bit region. And then to do that, we set the global G-bit as 1, and then only mark it as a writable, not for the executable at all. And then I previously described about the CR0 register. So this is the CR0 register for the features that we can enable and disable. So protected mode enabled, the PE bit is the lowest bit in the CR0 register. So that's why. So there could be some of the pre-configured value for the CR0 register. So when we update the CR0 register, we cannot do arithmetic operations on that. So what we can do is we fetch the CR0 value to EAX first, and then EAX, we can use the accumulator. And then we apply the OR operation with the CR0 PE on. So the value of this one is just 1. The reason why it is 1 is it will enable bit adhere. So for example, for enabling the MP, the monitor coprocessor, then we need to use the value 2 because that value is a 1 0 in bit pattern. So that the applying OR operation to the register will make the second bit up. Yeah. That's how we can enable the feature. And then so OR operation itself does not enable the feature because that is applied to the EAX register. So after we move that EAX register to the CR0 register, then the protected mode will be enabled. And then after loading the global descriptor table and then enabling the protected mode, then the JAWS code will jump using long jump to change their code segment and then running the protected mode code. And then prot mode CS segment, yeah, that is defined as 8, and then that will refer to this global descriptor table. And that's how JAWS makes a transition from the real mode to the protected mode. Then let's having a little bit of summary about the protected mode. So in the real mode, our address calculation model was like the segment multiplied by 16 and then add the offset. And then that will not be used after we enabling protected mode here. So, and then what it will do is like it will select the global descriptor table entry from the table and then fetch the base and limit and then try to calculate the address as a base plus offset, but the offset should be less than the limit. And then limit bits are 20 bits, but depending on the 1 and 0 of the G bit, that will define the granularity of the limit. And then because each entry size will be 8, so we will only use the index as a multiplication of the 8. So we will not use the last 3 bits, but we will use the last 2 bits in like all the segment register as the current privilege level. And then the flag part of the global descriptor table can store the data privilege level. And then we have a 4 privilege level, but we will only use 2 of them, 0 and 3. So the 0 means that the operating system and then has the full like the capability. And then 3 means that it has a restricted capability. And then how we can enable the protected mode is like the changing the CR0 register for that value. And then to change this current privilege level, we need to use the long jump instruction, but we can switch from 0 to 3, but we cannot switch 3 to 0. Any questions up to this point? All right. Then let me finish up for the virtual memory. So the rest of parts are more conceptual. So it will not having like a much more engineering stuff like the complex bit or like that kind of this stuff. So please be easy. So after enabling the protected mode, we will set up the virtual memory. So right now, all the addresses are physical. That means like it will directly work with the RAM memory. But before getting into the virtual memory, I would like to introduce why do we need the virtual memory in the operating system. And then the virtual memory has 3 goals. So we would like to have transparency and efficiency and some sort of protection by having the virtual memory. And then let me explain each of the property and goals by some of the examples. So suppose we have a uni-programming environment. What that means is that like we only have 1 program to run on a computer. So that's totally different with the current computing because like I'm not sure you might know about that. So if you try to check like how many tasks are running on your laptop, you can easily see like the 100, 200 processes are running all together. Yeah. So this is not the case, but let's make a simple case to like see that why do we need the virtual memory. So suppose we have an operating system in low 64 kilobyte, and then suppose we have one program to run. So it could have like most of the program has a stack and data and code area. So I just depicted in like the 3 different area. And then if there's only one program, we have the freedom, the program, like the writer, the developer of this program has the freedom to use any kind of memory region here. Then we are also assuming that the operating system only resides in this part, and then developer knows that. So the developer would not use this region, but can freely use like the rest of the region, something like this. Then we have some free spaces like this. And then suppose we have another program. So when we load the program 1, then the program 1 can use any kind of part freely because there's no existing program at all. But when we load the second program at the same time, so then right now it's a multi-programming environment because we may use like the several programs for the operating systems. In that case, to load that, we need to search for the free space that can accommodate in each section of the program. So these kind of the free space need to be big enough to contain each of the code and data stack area. So in this case, it magically fits with some other area, so we can load it. But what that means is that, so suppose the program 1 wrote in this way. So they will load in the 1000 for the code, 4000 for the data. Then when we load the second program developer must know that which address was occupied by the other program, and then they need to change where they should be loaded. So what that means is that depending on the system state, you cannot choose which address you will use, and then system will decide the address that you should use. So that means, suppose, so for here, like everybody uses like different programs for your laptops and then as an application. I use Beam as an editor, but the most of our students prefers the VS Code. So our editor is totally different, and then that means the memory usage will be totally different. Yeah. But how can we assume that as a program developer, what kind of the system configurations are available? It's practically infinite. Then we cannot assume that like what kind of address we should use. So like what we can do is like let the operating system decide about that. And let's take a look at another problem. So this is about the transparency problem. The implication is that the application developer need to know which address the application will be loaded, and then they need to consider what kind of other applications are running on the operating system if we don't have a virtual memory. And the second example is that suppose we have a free spaces like this. So I designed the second program to have as a sum of all the size, it should be fit into the sum of the free space. But the problem is that we don't have the contiguous space that frees up to 160 kilobyte. So in that case, even if there's some of the remaining space we can use for this one, we cannot run the second program. Maybe operating system need to shift this program data area a little bit, then we can fit the program code for the program 2 in here. But doing that requires also need to think about like depending on the system state, we need to move the things around. So that makes the things complex, because we can practically think of like there could be infinite number of like that kind of a state, and then caring about that kind of thing is quite infeasible. And then in this case, this is not efficient. So what that means is that like although we have a free space to accommodate as a summation, we have the free space to accommodate this program, but we cannot get them in because memory is fragmented. Yeah. So if there's an efficiency problem, and then another problem is that, so suppose we get the two programs runs like this. So program one is with this and this data, and then this stack, and then program two runs with this code, data, code, and stack. But suppose the program two, the developer made a mistake. They used more memory on the stack than supposed to do, then it will overwrite some of the stack of the program one. Also, if the program two's data overflows, then it may overflow and then touch the program one's data. Yeah. So what that means is that like if we don't have virtual memory, because physical addressing allows the programs accessing any kind of address, if the privileges are all same, then program may affect the other program's execution. But I mentioned that there is a privilege separation between operating system and then application, ring 0 and ring 3. But the application will all using ring 3. Then one application for the other application, they have no privilege separation. Then how can we protect against this kind of problem? But please don't worry, modern operating systems are not designed in this way. So that I just want to depict that some of the problems if we don't have a virtual memory. So the virtual memory has 3 goals. So the first example was like whenever we write the application, we need to think about like what other applications are residing in the memory. So the first goal is about transparency. So the virtual memory would like to give the transparent view. So for an application's point of view, so the virtual memory space is totally empty. So they can use any kind of address as if like they are the first one that is running on the machine. Yeah. So that we can give that kind of view and then that kind of the freedom to use memory by having the virtual memory. And then the second thing was efficiency. So efficiency problem happens when even like we have a free space as a sum, like we can accommodate the program size, but depending on the available contiguous space, we cannot accommodate the program, even if we can do. Yeah. So that kind of memory fragmentation exists, but we can resolve the fragmentation issue by using the virtual memory. And then the last one is about protection. So if the application runs on the same privilege level, then one application can touch the other application's memory. So we need to isolate that. And virtual memory can do that. And the mechanism to implement the virtual memory is so-called paging. And what paging here means is that, so in Intel machine, and then it's same across like many other architectures, so ARM, SPARC, or MIPS, or RISC-V, and there are many other architectures, but the modern operating system engineering utilize the memory as like the split into the page granularity. And then one page means like 4 kilobyte in size. So suppose you have like the linear memory like this, and then we will split each part of the physical memory as a 4 kilobyte granularity, starting from 0, 4 kilobyte, 8 kilobytes, something like that. Yeah. And then likewise, we have a global descriptor table to fetch the base and the limit address. We have a table, so-called page table, to indirectly mapping the virtual address to a physical address. And then let me show you that in some of the example image. So on the left side, I depict the virtual memory space. So for a program, so when you compile a 32-bit program with GCC, so it always assumes that your code address starts at the 8048000. But in the previous case, if we don't have a virtual memory, we cannot use the same address for different programs. If one program occupies that address, we cannot get in there. But in the virtual address model, that doesn't matter at all. So while we are giving the full freedom, so all the application will use 804.8000.900, this kind of address for their code and data. But what we will do is we will have a table, the interaction table, that this address, virtual, will be mapped as a physical address 1000. And then this address in virtual will be mapped as a 11000. But the good thing about having this kind of table is that we don't have to keep the sequence of these kind of addresses, because it's a one-to-one mapping between the 4 kilobyte region, which is a page. So although the program code are contiguous, we can put those kind of the pages in totally separate manner. And then we can even put the stack in between there. But what we should have is that, so we should have the correct table to indicating that which part of the page in virtual should be mapped as which part in the physical. And then suppose we are loading 2 programs at the same time. So this is the program 1 and this is program 2 and their virtual address space. So they can use any kind of address. So I make it as like that they are using exactly the same address. But what we can do is we will have a page table for program 1 here, and then page table for program 2 at here. So for the program 1's the program code 804.8048.000, that goes to the physical address 1000. But in the program 2's point of view, that address goes to 13000. So here. So by having this kind of the table that redirects the virtual address to physical address, we can give the transparency to the program. So now the programs don't have to worry about like where it should reside. So that they can program at their own memory use. Then the operating system can create this kind of table to spread out the pages accordingly to fit into the memory. And then next is about the efficiency. So there was a case that like some part of the code need to be contiguous in physical memory model. But by using the virtual memory, we can split this program code apart like this. So they're definitely a fragmentation within the page granularity, even with like the virtual memory. But we don't have like the problems like we cannot fit like the big contiguous space into the physical memory, because some of the memory that is virtually contiguous don't have to be contiguous in physical. What we need is like we need to have this kind of table that makes those kind of view as contiguous. And the last case about the security. So there was a case that if this kind of the stack overflows, what happens was in the physical memory model, stacks were like allocated somewhere in the adjacent, then like overflowing from one program will affect to another program's execution. But in the virtual memory model, they will have a different table. So in their virtual memory, they don't have any address mapped at here. So what that means is that in this kind of table, there's no entry, and then CPU will just generate fault on it. So by separating the virtual memory space, we can naturally isolate one program from the other. So we can get some property of the protection that like if there's no mapping, then they cannot access. Then by using the virtual memory, we can isolate the applications and memory from the others. Any questions about the virtual memory? Because I just introduced the concept of the virtual memory, but in the next lecture, I will go over the more detail about like how we can implement this kind of virtual memory system in the operating system. But just for the conceptually, is there any questions about like having this kind of table to disjoint the virtual address from physical address, and then releasing the requirement of the contiguous space or something like that? There's one question. So it may affect the performance of the application. For example, so suppose you have a server CPU, then the server CPU will have like each CPU has its own RAM. So like suppose you put like 4 different CPU. It's not about the multi-core, 4 different CPU package. Then you will have 4 sets of the DRAM. And then access time from the closed DRAM is much more faster than the far DRAM. Yeah. So in case like if the physical memory was used to put on the sparse across like the multiple RAMs, then it could be slower. And then there must be some of the optimization techniques to like gather all the things near the processor. Yeah. So that there could be that kind of issue. But in a single CPU model, yeah, that kind of delay is quite negligible. Yeah. So like we didn't care about that here. Right. If there's no more questions, then let me finish the lecture here, and then please take a look at this diagram. And then this diagram is very important. So whenever there's a CPU gets in the address, it will get the segment and a segment selector and offset. Then it will translate the address using global descriptor table. And then next lecture, we will learn about how the page table translation goes on. And then this part describes how the virtual to physical address translation happens. So this is also available in our course website and then slide. So please be prepared to get this kind of image in your mind when taking the lecture for next week. Yeah. Thank you, and then I will stay here for 5 to 10 minutes to ask any questions.